making a video for the DraftScience channel and gravitational waves. Yeah, this really is just so bad. Anyways, this is the press conference, and they're playing a video at the press conference. And alright, so yeah, I didn't think to turn the camera on for the intro, but they're just so oh, we were so sure this was a good investment. Anyway, National Science Foundation. Anyway, alright, so I'm not blaming Einstein for this total butchery of concept, but they don't even understand what a gravitational wave is. So this is what I didn't know. This was a National Science Foundation representation. I mean, it's just so ignorantly stupid. So first, conceptually, it doesn't make any sense in the sense that these two things are spinning, and this is the wave being created. They're saying this. It's an upward bulge in space-time. That's how they've drawn it. Which doesn't make any sense, right? I mean, gravity, dense space-time, right? Isn't that conceptually the way it's supposed to work? It puts a dent in it. So they don't even have the relief correct. Second, gravity doesn't trail something in a crooked line. Gravity isn't gravitationally gravitized in some way. So this isn't even the mechanism of gravity. Certainly it wouldn't propagate at the speed of light this way. If you did this to it as the wave, quite obviously this stuff would be moving the speed of light, and it would take forever and ever and ever and ever to get to us. So it obviously can't propagate this way. It's a completely inaccurate drawing. Like I said, I won't blame Einstein, because I'm pretty sure Einstein was smart enough to figure out that if you do this to the speed of light doesn't get here as fast. Especially when this starts getting really wide, it would take a million years just for it to get one wave. You'd use up a million years of the speed of light just to get one wave accomplished as it moved through space. So it could never get here if it worked that way. And obviously it doesn't work that way. So this drawing is just so wrong. What's happening is these two things spin around each other, facing us. There's a point where they're both behind each other, which means the mass is essentially doubled from our perspective. And then when they're this way, their mass is halved. You know, it's still a strong mass, but it doesn't have the same peak. And so what's really happening is the wave is just the deficit in what would be space-time if there's such a thing existed. But it's a straight line force. There's none of this. It's a straight line force, and it's on, off, on, off, on, off. Because as this turns, it's half gravity, then it's full gravity, then it's half, then it's full, then it's half, then it's full. I mean, double, single, double, single, double, single. That's the wave. And it's a straight line force moving the speed of light. I mean, this is just fundamentally inaccurate. Even if you believe in space-time, this is the wrong way to describe it. This is the stupidest thing I've ever seen. There's no evidence that gravity does this. When the Earth's going around the sun, it's not leaving a crooked dent in gravity space. It's a straight line force. Physics. I mean, shit. Alright, so let's play some more.
The gravitational wave stretches space in one direction and compresses space in the other direction.
Okay, so stretches space in one direction and compresses space in the other direction. That certainly doesn't tell you anything now, does it really? Come on, seriously. Seriously. It just means that from this angle, at a moment in time, the two things are lined up. From this perspective over here, they would be exactly the opposite. So it's sort of like it's like a lighthouse, okay? It's on here, and then it's off over there. And then it's on over here, and then it's off over there, you know. So silly.
You really believe that you could ever detect them because the size of the effect is so small.
So that made sense, showing atoms. That makes the size of it look like that's a proper way of perspective. You know, instead of just pointing out that, like the light that comes from a galaxy, the galaxy produces, you know, 1 gazillion lumens, and you know, by the time it gets to us, there's only, you know, 4 lumens. Yeah, that's our share of the zillion lumens because we're so far away. Inverse square law. But instead, this is what they do, whatever this means.
I came to the conclusion that, yeah, if you made this long enough,
Nobody had ever made something like this before, so there was a lot of technological challenges that needed to be overcome.
That's what scientific discovery is really all about. You don't choose the simple things to do.
Yeah, but if you don't understand them, then they can really be complicated. Alright, so and again, what are they doing? What exactly? They're looking at a big hunk of the sky. No lens to this thing at all. It can't focus on anything. And they're seeing if there's some double dent in gravity. And it's really just looking for that double dent. But it could be caused by many things, theoretically. You know, I mean, a bunch of just a happenstance of there being a lot of mass in one location in the universe that fluctuates. You know, moves past each other regularly. Yeah, those waves wouldn't be regular enough. So, let's see how regular what they found is. 1,000 scientists, 16 countries, 25 years of lots of money. Yo, wow. That makes you feel good, right? 1,000 scientists for 25 years. Let's add that up.
we have done something which is brand new.
The field is busted wide open.
It's monumental.
Really, and again, I can't for the life of me understand why this could at all be useful or significant. You won't be able to resolve anything out of this. It's useless. I mean, you have a better chance of seeing the stuff you're seeing the gravity from than actually feeling the gravity from it. Silly.
It's like Galileo using the telescope for the first time.
I looked at it, and I thought, my God, this looks like it's it.
Back to the press conference. Okay, here we go. Mr. Scientist now. Do I talk now? Is it my turn? Do I get to say my name and stuff?
Ladies and gentlemen,
Yes. They look like they're all gentlemen, actually.
we have detected gravitational waves.
Yeah.
We did it.
Oh, we did it. Yeah, it was just so cool to have that moment where I could say, we did it after all that money and everything. We really did it. And I'm pretty sure this time it's not a cat like bouncing on the roof this time. I mean, I know there's a couple of false alarms and all that, but you know, I'm sure we did it this time. This time it's the real thing. I'm sure. I'm pretty sure. Yeah, very exciting. Ah, there, we do have a lady there. Okay, just verifying. Oh, please.
I am so pleased to be able to tell you that.
Yes.
So these gravitational waves were produced by two colliding black holes that came together, merged to form a single black hole about 1.3 billion years ago.
Do you have the picture of them, please? Can I see the picture of them, please? Please? Photons move just as fast as gravity waves. Well, by your wrong drawing, no, photons would move about 10 zillion years faster.
They were detected by LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO is the most precise measuring device ever built. Let me start with what we saw.
Yeah, really. It's more precise than that Hadron Collider.
So on September 14th, 2015, the two LIGO observatories in Hanford, Washington, and Livingston, Louisiana, recorded a signal nearly at the same time, nearly simultaneously.
Okay, so 2014. So September of 2014. So let's see, that's a year and a half ago. One signal. That's not too good.
Simultaneously, and the signal had a very specific characteristic. The characteristic of, as time went forward, the frequency went up. And what was amazing about this signal is that it's exactly what you would expect, what Einstein's theory of general relativity would predict for two big massive objects like black holes spiraling and merging together. Now, it took us months.
Yeah, well, we'll have to see what the evidence really is. You know, the frequency of black holes spinning, I just don't know how fast you can get that up to. See, I thought they could find something that was in a spin that was a little bit slower, so then they could verify it by going to the same location the next day, you know, and see if it get the same signal the next day. That would be nice.
Of careful checking, rechecking, analysis, looking at every piece of data to make sure that what we saw was not something that wasn't a gravitational wave, but in fact it was a gravitational wave. And we've convinced ourselves that's the case, and we're here to announce that today. But I do want to...
Okay, so a year and a half. It took them a year and a half to verify that we can't really explain this any other way, so this is what we're going to say it is. Not terribly impressive.
There's something else. This is not just about the detection of gravitational waves. That's the story today. But what's really exciting is what comes next. And it's 400 years ago, Galileo turned a telescope to the sky and opened the era of modern observational astronomy.
Yeah. You know, it's kind of disgusting that, you know, if you ever get into the science game and you get a name, they're going to keep dropping your name in circumstances where you might say, I don't endorse this nonsense. I mean, I wonder what Galileo would say to the significance of gravitational waves. I wonder what he'd say to the whole idea of bent space-time.
I think we're doing something equally important here today. I think we're opening a window on the universe, the window of gravitational wave astronomy.
Right. Again, I just can't possibly see how it could in any way mean anything at all. Be at all useful. But whatever, that's me. Guess the thing to do would be for them to find the double black hole. Yeah.
So I'm going to show you two videos that are going to sort of tell you what we discovered. So the first video is the two black holes. So
okay, this I'm going to like, because now I can see whether these are up signals or down signals. Maybe, I don't know. I mean, again, like I'm saying, the real key is the absence of gravity, right? Gravity is an absence mechanism, not a positive mechanism. So it almost should look like a silence is what you're detecting.
What you're looking at on the screen here are two black holes. Each of them are about 30 solar mass, have about 30 times the mass of the sun. All right, and you're looking, the black holes are the black things in the middle, and you're looking at the stars behind them. By the way, this is not a Hollywood production that I'm going to show you.
Oh, this is already a Hollywood production. Newsflash. This is not a real image. So, you know, I mean, how can he start with, this is not a Hollywood production? Well, of course, this is an entirely fake image, never ever resolved by any optical device ever. Okay, anyway. I mean, well, I have to play this part, and then I'll, you know, go back to listening.
Real computer simulation solving Einstein's equations for these merging black holes. So this is really what it would look like if you were in a spaceship.
Well, I mean, this is just so fucking goddamn obnoxious. I mean, this is not a Hollywood production. It's a computer simulation. Oh, fuck. I mean, goddamn, is that ever grotesque?
Up. And I will also point out that the movie I'm showing is vastly slowed down relative to what happened here. So let me start it. All right, you can see that as the black holes spin around each other, all right, the stars behind them are warped, and that's because the strong gravitational fields bend the light that comes around.
Right. I mean, shit. Shit. Yeah, that's all you can say, right? Yeah, that's all I can say is shit. Evidence where? Never. Oh, so pathetic. Alright, anyway. It wouldn't be lensing the stars around them. He didn't even say that right? It would be lensing the stars far behind the black holes, not the stars around the black holes. It would be consuming all of that. So anyway, so this is Einstein's math, he's saying. So Einstein's math permits this line here, apparently. Whatever this line is, where this stuff doesn't get sucked into either one of these gravitational wells. It just sits there and says, I don't really care what you two black holes are doing. You're not relevant to me at all. Somehow that's possible.
But what
I mean, look at it. I mean, this is he called this not a Hollywood production. And this simulation, in my opinion, looks like, well, let's just take a couple of Blender images and put them on top of black holes in like pea soup, and then we'll superimpose the star field on top of that. That's all this is. This is shit. Yeah, this is really bad.
Pay attention to in this video is the fact that as they orbit, the black holes are getting closer and closer to one another. The orbit is speeding up, and eventually they're going to merge. The event horizons are going to join.
Right. So he said that was grossly shortened, or whatever he called it. Yeah. Well, but let's. Who says gravity works that way? But anyway, okay. Let's just assume that that's. So it's like stuff going down the drain. You know, just as a spinny thing, but it's really not the same as a drain.
Boom. They produce one big black hole.
I mean, they do gain more and more velocity as they get closer and closer together. It really wasn't illustrated there at all.
Which relaxes. You see a little bit of vibration there. It becomes two smaller black holes die, one bigger black hole is born. Now, what's really amazing about this is the first time that this kind of a system has ever been seen. A binary black hole.
Well, let's understand. Nothing was seen.
Merger, and it's proof that binary black holes exist in the universe. So,
okay, and this is proof. So he says they have proven the existence of binary black holes. Okay, well, I don't know. It seems a bold statement.
I want to put this in perspective for you because I think it's very important, all right, to give a sense of what really happened here.
Right. This is somehow he tells us that this event was isolated in a field of the universe. So a whole section of the universe, for this one moment of time, this had to be the only noise coming. Couldn't have been any other galaxies doing anything or forming. Nothing else could have been going on, or you wouldn't get this clean signal. So somehow he caught the universe on a quiet moment.
So each of these black holes are about 150 kilometers in diameter, a little bit bigger than that. Take something that's
150 kilometers. So somehow he knows that too. So now we're back to we're all the way to I can make super compressed matter. Yeah, no problem. 150 kilometers that have 1 billion suns worth of energy in them. Just why don't they bring the Pope out and let him tell me some stories next?
150 kilometers in diameter, so that's about a little bit bigger, maybe a lot bigger than the metropolitan Washington, D.C. area. Pack 30 times the mass of the sun in that.
All right, 30 times. That isn't very much. 30 times the mass of the sun? The sun doesn't even weigh... the 30 times, the sun and the mass, this is kind of an interesting little fact, but, the planets, if you add up all the planets and their mass, I think it's more than the sun, actually. The sun's not all that massive. So something only 30 times the mass of the sun, I'm supposed to believe something only 30 times the mass of the sun, produced a gravitational wave that traveled 1.5 billion years across the universe. I don't think that happened. I think that's you've just made a silly error or something.
Accelerated to about half the speed of light. Now take another thing. 30 times the mass of the sun. Accelerate at half the speed of light and collide them together.
And they become then 60 times the mass of the sun. So 60 suns. I'm supposed to believe that the gravity from 60 suns, the gravitational effect, traveled all the way to the Earth and bent the surface of the Earth. I mean, it didn't make a photon in a telescope. No, it's produced so much energy, it bent the surface of the Earth. Science really has just left the building, right? There's no rationality to this, right? There's no what are they saying? There's a whole bunch of dark matter on the way here that kept re-energizing the gravity from 60 suns. Something as small as 60 suns. He did say 1.5 billion light years away, or didn't he? No. I don't think Einstein said you could do that. I don't think Einstein said you could do that.
That's what we saw here. It's mind-boggling.
No, it's mind-nauseating.
All right, now, let me talk about the gravitational waves. You didn't see any gravitational waves there. What you saw was after the black holes. Now let me look at this.
Yeah, no, I didn't see anything. I saw a fucking piece of shit you made up. That's what I saw that you said wasn't a Hollywood production, but was obviously a Hollywood production. That's what I saw.
From the gravitational wave perspective. So you're going to see, again, a computer simulation. This is a
yeah, again, some more Hollywood production.
real simulation using Einstein's equations.
Yeah, some of them maybe. Yeah, I don't know. Let's see how bad this one is. Oh, shit, this is so painful.
You see the two black holes. And the green that you see are the gravitational waves that are produced as the black holes orbit around one another. They're orbiting.
Again, so again, we're supposed to believe that gravity is not a straight line force. So that somehow as these two things spin, the gravity lags behind and bends. Total bend of the gravity somehow. And that's what's creating this wave. But that, again, how can you people, I mean, somebody's got to say something like, well, wait a minute, if gravity is traveling the speed of light and you go around in this wave, it can't get here. It will move too slowly. You can't see how much longer this distance is. If you move this distance at the speed of light, right? That's a lot longer distance than from here to here. Damn.
K's and they merge together. So they're spinning around. You see they're getting closer and closer together. As they get closer and closer together,
It's just such a misrepresentation of this. What's happening? This is just so bad. Anyway, there's no point in me saying this is so bad. Is it just so bad?
there are more gravitational waves. They merge, and there's this burst of gravitational waves that travels for 1.3 billion years. It passes through everything. It goes right through matter, right through stars, and it eventually gets to the Earth.
Right, but it's gravity. Like photons, it's dissipating by the inverse square law, by the very same inverse square law. So for every bit of time it's traveling, it's getting weaker and weaker and weaker and weaker and weaker as a signal. And we're supposed to believe that when it got here, I mean, from my theory, gravity's just these photon things, you know, gravitons. We're supposed to believe that they bent the surface of the Earth.
All right, and when it gets to the Earth, the gravitational wave passes, and what it's going to do is stretch and...
Well, there you go again. So they showed you the little blue, the green thing going by, but actually it's a deficit in the gravity. You wouldn't, if this stuff is true, if it happened, it's not a bulge in anything called gravity. It's a deficit in the field force. So it's a negative that does actually hit, not a positive.
Press space as these waves pass, and you'll see that the Earth is jiggling like jello. I don't want people to be scared here. The Earth doesn't really do this. This effect is greatly exaggerated, but it gives you...
Right, no Hollywood effects involved whatsoever. It still just doesn't make any sense. Yeah, it doesn't really make any sense. Gravity don't do that. 60 suns. So again, 60. So essentially, he's saying 60 suns produces enough gravity to bend the surface of the Earth. 60 suns, billions of light years, a billion light years away, produces enough gravity at this location to bend the surface of the Earth. It converted from 230s to 160, and that conversion somehow created enough gravity, some sort of extra gravity, no, there's no such thing as extra gravity, to bend the surface of the Earth.
Effect. And then we zoom in, and how we detect these are using the interferometer that's in LIGO. And Ray Weiss is going to tell you more about the interferometer.
I predict there will be some scientist with a little bit of integrity somewhere that's going to point out this is theoretically nonsense.
I just want to say one thing, that the effect...
I mean, if they were talking about a black hole, you know, like the ones that bend little clouds here and there, and it's got 1 million suns in it, well, you might stand some chance here. But you heard him. 30 times the gravity of the sun. 30 times. How can this make any sense?
That we're trying to measure from these violent, these big black holes colliding each other at half the speed of light, all right, is so tiny that it takes something like LIGO to measure it. We are trying to measure things basically at 1/1000th the diameter of the photon. That's the size of the signal that you see on Earth from those events.
Well, I mean, to say something like that's the size of the effect, I'm just saying that obviously the size of that effect over the surface of the Earth, I mean, moving the entire Earth's surface, even one photon of, bulge, you're still talking about this entire mass, going this length. And how deep it has to do that for the whole surface to move. I mean, get real. That's a lot of energy. So again, we have magical energy again, don't we? So why don't we use gravitational lensing? Why don't we just make an energy producing device and collect gravity from 30 sun black holes, to run our industry? Why don't we just make a big giant, metal rod, and then we'll bend it and create electricity at the two ends? Shit.
Take place 1.3 billion years away. All right.
What did he say? Damn, I missed it. But something billion light years away again, right? So a billion light years away, and it produces enough gravity at this location to bend the surface of the Earth. 30 suns. 60 suns. 60 suns have the ability to produce enough gravity, even in their death, to bend the surface of the Earth from 1 billion light years away. Bullshit.
Put that in perspective, because I think those kinds of numbers are hard to get your head around. All right, if we were trying to measure the distance between the sun and the nearest star, which is about 3 1/4 light years away, LIGO is capable of measuring that, if it could do that, to a level of about the width of a human hair.
If it could do that, so whatever. Well, again, I don't buy it, but whatever, fine. He says it's so accurate that yes, we can hear Tinkerbell slipping her panties on.
So the width of a human hair over 3.25 light years. That's remarkable precision. Right. Now what LIGO does,
I think made up, but fine, whatever.
is it actually takes these vibrations in space-time, these ripples in space-time, and it records them on a photodetector.
Okay, he calls them ripples in space-time. Now, does he have any evidence that it's space-time? That's not what they're detecting. They don't have a space-time detector. So again, it's just extrapolation that's totally unnecessary to being accurate. What's being accurate is we're detecting movement in the Earth and assuming the movement's being caused by something out there bulging the Earth.
And you can actually hear them. So what LIGO has done, it's the first time the universe has spoken to us.
Oh, this isn't at all a Hollywood production. Let's keep remembering, this is not a Hollywood production. We're giving voice to the universe. The first time ever here, you can hear the universe talking to you. La 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 la.
And this is remarkable. Up till now we've been deaf. Gravitational waves, but today we are able to hear them. That's just amazing to me. I think this is big.
Fuck! This is not science. This is propaganda.
Again, because what's going to come now is we're going to be able to hear more of these things. And no doubt we'll hear things that we expected to hear, like binary black holes or perhaps binary neutron stars colliding. But we will also hear things that we never expected. And as we open a new window...
Yeah, like what? Tinkerbell slipping on those panties. Woo! Woo!
In astronomy, we may see things that we never saw before. So,
yeah, I wish you could see what's in my mind. I wish you could read my mind.
Let me conclude by thanking the National Science Foundation
for the huge giant paycheck they've been giving me for decades to play this idiotic role of propagandist for bullshit. Thank you very much. I really enjoyed it. I really enjoyed just screwing you for big bucks while I do just silly nonsense. Thank you very much.
For 40 years, since the NSF started funding Caltech and MIT to do pilot experiments for LIGO, and then in 1992, the NSF
no doubt poisoning some water and whatnot.
went ahead and funded the LIGO project.
Irradiating a few poor people.
And they took a big risk. All right, this was bold. The science was solid.
Right. It was bold. Was a big pile of money, and what are you going to make out of it? Oh well, I don't think absolutely anything. And I frankly don't even think you have anything. You're 30, 60 sun frickin' billion light years away, gravity wave. I think is a fantasy, buddy.
We didn't know how many events we would see. The technology was nowhere near developed. This was truly, I think, a scientific moonshot.
Yeah, it was a truly, no, it wasn't a moonshot. I mean, that was all figured out pretty goddamn good. They modeled all kinds of things. They shot, oh shit, it broke. Oh, hey, you gotta put some better glue on that when you make the real one. You know, they did all kinds of modeling for that. This is just a complete fucking, this is just a sacred money cow. White elephant that you're all just making a nice living off of. Elitist pricks.
Really believe that. And we did it. We landed on the moon. So I really want to thank Dr. Cordova and NSF. And also...
I mean, comparing this to landing on the moon is just, oh, that's just throw up worthy.
U.S. Congress, taxpayers have supported this research because it's really gotten to the point now where it's going to take off.
Oh yeah, it's going to take off. It took us only a year and a half to verify that our result wasn't, you know, a cat on the roof. Could have been a fox, but we're not going to talk about that because we don't think there's any foxes in the area.
So I'm going to conclude my remarks, and I'm going to introduce my esteemed colleague, Gabby Gonzalez. Gabby is a professor at Louisiana State University. She's also the spokesperson for the LIGO Scientific Collaboration, and she's going to tell you more about this event and about the team that discovered it and about the observatory. So
yeah, so interesting. All right, anyway, so I won't bore you with playing the whole thing. I've seen her before in a couple of these TV shows. Gabby. This is just such a crock of shit. I should see. Well, I'm just not gonna stand going through all the people and the this and that. But if they do this thing again and somebody corrects somebody and says, "Oh, we didn't mean 30 suns. We mean 30 billion suns or something." Maybe there'd be a correction somewhere. I mean, really, just think about it. 60 suns worth of gravity. It can't possibly make a wave that we could feel here a billion light years away. It's just not possible. Anyway, till next time. I mean, it has to move the surface of the Earth. I mean, it's a lot of gravity. I mean, we could put something really close to the Earth, like, a quarter of the moon or something. I mean, it couldn't do this. Something really close can't do this. Till next time. Back. I guess I'll play a little bit of this, but okay, so they have two of these things, one in Washington, one in Louisiana, and so apparently they have to hear the same signal at both of these stations. So really what has to happen is that like the entire continent of the United States has to vibrate. And this is being caused by something over 1 billion light years away that's only 60 times as massive as the sun. And I'm to believe that if I built something like that, a black hole, and I blinked it, just turned it on, off, on, off, on, off, here, gone, here, gone, here, gone, that they could detect that by how much it changes the ground on the Earth. I just don't think that's possible. Yeah, no, I don't think so. Anyway, and here's some of this mush.
Detectors are L-shaped. This is the LIGO Livingston detector. They are 4 kilometers long on each side. That's a Hanford detector. And we have lasers that go back and forth between mirrors to measure the distance between those mirrors. And gravitational waves would distort the space-time and would be measured as distortions in that distance of 4 kilometers. Again, it takes a lot of people to do this, and you can see a lot.
Yeah, well, I can see kids here, apparently. So, yeah, they're saying that they obviously these are visiting students or something. Anyway, the whole thing does not make a hell of a lot of sense to me, because I don't know why okay, I kind of, I'm big on this whole perpendicular thing, so it's doing the perpendicular thing, but I really don't know how that's going to help them in detecting the whole continent moving. Nope, who knows?
The people, young people doing this, as well as people who have
yeah, young people doing this. Yeah, I don't think they were doing anything. No, I think it was just some silly thing where you get paid some extra money if you let some students in.
Working on this for decades. So this is it. This is what we saw. Okay. September 14 last year, we saw this.
September 14, no. Last year, no. He said 2014. So, I don't know. That's accurate.
Signal in Livingston, Louisiana. That is a measure, that's a waveform that we saw. The units are strain, that's a distortion of space-time, and you can see a peak value. The largest value of this waveform was a part in 10 to the 21. For 4 kilometers, that's a tiny, tiny fraction of a proton diameter. That's incredibly tiny.
Okay, tiny fraction of a proton's diameter. So, yeah, well, let's, I don't want to go into the logistics of saying, gee, I don't know. You can move light across 4 miles back and forth, and you can measure a difference in a half of a proton.
But this signal is seen, you can see it even by eye, above the ever-present rumbling noise that we have in the detector. But we know it's real because 7 milliseconds later, we saw the same thing in the Hanford detector. This is it. That's how we know we have gravitational waves. But we know a lot more than that. You can see that these signals have oscillations that grow in frequency and amplitude and then settle down. And that's exactly the prediction that we know from solving Einstein's equations on computers for the coalescence of two black holes, merging into a larger black hole and settling down. And
right, so their argument is that when that happens, that there is some phenomenon that creates some sort of extra burst of gravity somehow. I would argue that I don't think there is any such science to defend that, but whatever. Whatever. You know, it's proof. Okay. I've heard that word before, proof.
You can see here overlaid the template that we used, or the numerical relativity simulation that was done for the coalescence of these black holes.
Yeah, you could have given us a break and actually overlaid them in different colors, but whatever. So they overlaid them in the same color. Yeah, okay. Whatever. Fine.
That's how we know not only that we detected gravitational waves, but these waves were produced by the coalescence of black holes.
Right. So apparently it takes 7 seconds of Earth's rotation. No, that wouldn't work. Well, anyway, 7 seconds difference. So I have to figure out what that means geographically. Why there would be a 7-second difference in when they were received. Certainly couldn't be the rotation of the Earth. So what could be accounting for a 7-second delay?
So,
I mean, that sounds like a feature like an earthquake or something. Might take 7 seconds to get from one location to another location. But that doesn't make any sense. Both of the locations should be feeling the same effect. Technically. Should.
These are the fantastic news we're telling you about.
Okay. So, I mean, what was your next closest one? I would just be curious to see what the non-gravitational waves look like. Like the best result you had that was closest to almost being one. Be interesting to see.
Now, from these waveforms, you can tell a lot more.
Oh, there. I see they had the 2-color image. Why didn't you just use that before? So there they are, overlaid in 2 colors.
You can tell from the frequency the masses of the initial black holes. They had 29 and 36 solar masses from the fitting to the
29 and 36 solar masses. So I just don't understand how they can say they can detect that, but okay, whatever.
Numerical relativity waveform, we can tell that when they merged, they formed a larger black hole, but not with the sum of the 2 masses, with only 62 solar masses. And that's because...
Only 62. Well, 62 is... what? That's 4 short. Yeah, so obviously, I guess when they collided, they lost some mass somewhere. Oh.
There were 3 solar masses emitted in energy, in gravitational waves. That's
okay, so 3 solar masses were emitted as gravitational waves. So now it's real energy. So now, for the first time I've ever heard of it, you can actually create some kind of gravity. I mean, that doesn't even make any sense, right? They're photons. They have to be photons of some kind. Tons. Gravitons. But anyway. So, yeah, so if you want to say you detected an explosion of 3 suns exploding. That might make a little more sense.
Huge amount of energy. And we can tell all of that from this tiny fraction of a second in the waveform. We can even tell more than that. From the amplitude of the waveform, you can tell how far away this system was. It was more than 1 billion light years away. This merger happened 1.3 billion years ago, when multicellular life here on Earth was just beginning to spread. And
yeah, we know what 1 billion years is, you know. It's going to blow your brains out.
The signal took 1 billion years to come to Earth and produce this tiny distortion in our detectors that we are very proud.
Yeah, it's a tiny distortion in your detectors, which equals a huge distortion in the surface of the Earth. The movement of many tons of Earth.
To measure. Now, you can read a lot more details about these things in a paper that has just appeared online, peer-reviewed in Physical Review Letters. We are also publishing a lot more details in other papers that will be made public.
Well, how interesting. We'll see how it all plays out. Blah, 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 blah. But let's all have a spectacular parade for today. I'll be back. Oh, nice bit of theater here. First they convert into colors, and now they're going to convert it into sound. No Hollywood here at all.
Now, I wanted to play the gravitational wave for you to hear, but it's so short that it's just a thump. So what we have done is taken the real signal and shifted a bit in frequency, but it's still the real signal.
Hey, it's really something, huh? Anyway, I guess the real deal is here. So it's this little, as the wave gets closer, this is the thing they're looking for. So apparently it's not the height of the wave, it's the closeness of the waves that are their little blah blah blah, and it's this little chirp here. Apparently this is the little chirp she's looking for. There's no chirp in this one. That's sort of funny. Yeah, there's a chirp missing over here. Chirp here, no chirp here. Anyway, so very depressing. Anyway,
you hear the chirp?
Yeah.
There's a rumbling noise, and then there's a chirp. Let me do that again.
Oh, I don't have to do it again.
That's the chirp we've been looking for. This is the signal we have measured.
Yeah.
We can even tell more.
Okay.
Because we have two detectors, it's like having 2 ears. We can localize the signal. Not very well with only 2 ears, but we can tell it came from the southern sky in the rough direction of the Magellanic Cloud, and we could have a broad area, a broad uncertainty area for the region. Of course, the source is a very point-like source. I mean, the merger happened in a small region, but we cannot tell exactly where it happened because we only had 2 detectors. But this will get better. We will have a network of gravitational wave detectors. GEO 600 has been working for decades as a technology demonstrator, but Virgo is going to come with a sensitivity closer to the LIGO detectors later this year. So we will have 3 years to localize the signals.
Right. Across the Earth is round, by the way. I don't know if they know that, these scientists. But I would argue, I think it's going to be pretty much impossible. Yeah, pretty much impossible to get a signal on both hemispheres at the same time.
And later on, we hope to include in the network the Kagra detector in Japan, and hopefully one in LIGO, India, very soon. So this is just the beginning. We discovered gravitational waves from the merger of black holes.
Right, none of that's based on any conjectures or bullshit or made up stuff. It's all real, real, real. So, yeah, eventually I guess I have to try to find where Einstein predicted any of this crap. I think they're just saying that this is what we've done to Einstein. So I think it's another thing like with the gravitational lensing. You know, they say it's Einstein's lensing, and it has absolutely nothing to do with anything Einstein predicted. Einstein never predicted lensing in the arms of galaxies. Ever, 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 ever. But anyway. Yeah. Alright, so I'll play some. But no Hollywood here at all. No. Color and sound. No Hollywood going on. Okay, anyway, so yeah, the press conference has started. Oh, jeez. Alright, so this thing happened, well, yeah. Einstein would be beaming. That's one of the claims. I'm not too sure. Hug. Lots of hugging. So anyway, this was apparently a test run that they got this signal. Still not sure what year, because I thought the guy said 2014, but I guess it was September of 2015. Apparently. Let's see. Relieved taxpayers. That was even spoken. I mean, well, I'm just saying, you know, these are the kind of things you just shouldn't be saying at the press conferences. Something about how relieved the taxpayers are that you found this thing that you were supposed to do with all this money. It just sounds like maybe you forced it a little. So we'll see new, right? We'll see a new way. And the whole premise here is the only reason why they know they saw something is because it looks like the simulations. See a problem with that? We're seeing something new, yet it looks just like the simulations. Anyway. Inverse storm. What did I put that down for? Inverse storm. Storm. Infer. Oh, they infer. I thought this guy. Infer. Use the word infer. We infer the storm. We infer that, you know, as soon as they start saying infer, you know, that's just not a really great word for this kind of thing either. So anyway. So there's just this little, whatever, you know, this little noise. Blah, blah, blah. You know, like the needle on the seismograph. Jiggle, jiggle. I'm still not sure the 7-second delay between the two places getting the same signal. But I don't know enough about how the angle is of this thing they're receiving. But anyway, so they get the last cycles of this thing. They say they could give us more, maybe. You know, and then it goes to this last thing, and then they get this boom, or whatever, burp or belch or whatever. And somewhere in this last 0.25 of a second, there's some sort of release of 3 suns worth of something. Okay, now they're saying it's not electromagnetic in the sense that you're not going to pick it up with radio telescopes. So they say maybe, maybe not, maybe, who knows, right? So I mean, the idea is that there's a huge conversion of real matter into bent space. So this is the part I like. I mean, just because this is the part I I can use to my advantage for sure, because there's no other examples of this, right? Of actual conversions of where you actually get to see the energy of bent space. And so this is actually a conversion of 3 sun masses into pure energy in the form of bent space. Right? It's not electromagnetic energy, so it's not common tons. Certainly I could argue that if there are these gravitons, okay, extra pressure to the field, that's imaginable. But my argument would be, now we have to calculate if it's bending the surface of the Earth. So we have to figure out what, at 4 miles, what a half of a proton. So a half of a proton bend in the Earth at 4 miles. I have to figure out how much mass of the Earth that is. You know, we don't know how deep it goes is the problem. But it's a half of a proton worth of mass displacement over a 4-mile distance. So that's the thing we're after here. And so just to figure out how much mass this is. So I was wondering, why don't build these things in water, like underwater? Because they should be able to detect easier if they don't have to move as much mass to do the detecting, right? Seems logical to me. I mean, the moon moves the oceans up and down. Seems like the place to go. So, what else do I want to get to? Well, I'll get to it after this. Let's see what it is. Hello?
Hi, this is Congressman Rodney Freeling.
Oh, fuck you in the ass, Congressman. Fuck you in the ass, you fucking cunt. I didn't vote for you, you fucking cunt. Ever, you fucking cunt. You fucking bastard, retarded, shit for brain, fuckhead. I hate my congressman. I've never voted for my congressman, which means I don't really live in a representative democracy. I live in a fucking dictatorship by a bunch of fucking goddamn stupid majoritarian rule motherfucking cunts who don't want to give the minority the right to call them ass wipes. The cowards, white people, fucking cunt, little losery, small-willied white people who are afraid of giving away any of their authoritarian majority control. Although I am pretty much against all the dark people taking over. But I've never had a representative. That fucking cunt calling my house. How dare that cunt do that? I'm on the do not call list, douchebag. You ever read the federal law, ass wipe? Where was I? Oh, scientist. Yeah, there's no much better than politicians. Anyway, so it's non-electromagnetic photons. She didn't say the word photons, but I'm just saying it's non-electromagnetic. I would, you know, she said no X-rays. You know, but not that anyone was looking, right? So you don't know. There might have been. So anyway, I'm just saying, so you have 3 million solar masses worth of energy, which is a lot of energy. And that has been released by this thing 1 billion years ago, right? So I guess my argument would be, have we seen any evidence of gravitational waves? I mean, at a distance, right? So I'm just saying, let's go with a realistic distance. Something that's not 1 billion light years away. So let's go back to the real light bulb. The light bulb moment. Okay, so then now we're supposed to be having these light bulb moments happening in the universe all over the place, all the time. You know, a few times a day maybe. Who knows? You know, light bulb moments. Big millions of solar masses worth of gravitational waveness flies through the universe. Now, I would expect that at these half distances, right, it gets stronger and stronger and stronger, all that kind of stuff, right? So I'd be curious, you know, they showed this animation with a bunch of stars around these black holes. What happened to all those stars? Are they really going to make an argument to me that 3 million solar masses worth of energy pushed right through as a wave in less than a half of a second? So it's a half of a second, 3 solar masses. No, it's 1/4 of a second. 1/4 of a second, 3 solar masses worth of energy is going to go passing through things. So let's go see if we can figure out if that physics works. That anything could be anywhere near those things without getting annihilated by this wave. Is there any evidence of the annihilation? A hole where the black hole was. Right? Because that's sort of what you'd have to expect, isn't it? Come on, realistically? Wouldn't there have to be a hole where these 2 black holes were? Because it's like supernovas. You know, when supernovas blow up, they blow everything out of the area. Alright. I'm just saying, and this isn't even like a supernova. I mean, this is so particulated that it's all the way back to gravity. It's not even electromagnetic radiation. So, well, anyway, I'm a little suspicious. Yeah, that's who I am. I'm a little suspicious. So anyway, so then they asked this silly question about time travel and stuff. And so this guy, who had something to do with the stupid movie Interstellar, which, oh yeah, that just gives him all credibility. Isn't it all over the place? Interstellar, I mean, I haven't seen it, but it's obviously preposterous from the clips I've seen. Absolutely insanely stupid and retarded.
Deeper understanding of how warped space-time behaves when it is extremely warped, when it is what we call in the nonlinear regime, and highly dynamical and with very high speeds. I don't think it's going to bring us any closer to being able to do time travel. I wish it would, but that's a different direction, and LIGO is heading in LIGO's direction is really understanding the wild dynamics of highly warped space-time.
Yeah, well, whatever. Again, who cares about warp smorp, right? It's about what the energy is, isn't it? I mean, please. So you had 60. So, you lost 3 solar masses worth of energy in a quarter of a second. So that's the thing to figure out. What's the implications of 3 solar masses of energy? How bright a light bulb is that? Yeah. And it bent the Earth 1 billion light years away. Well, that's their argument. Just doesn't sound quite right. Anyway. Yeah, so next time. Ah, okay, this bit I think I would like, so I'll play it. Because he says something that's just, yes.
First of all, congratulations on this amazing accomplishment. I'm struck by the fact that, for the first time, humans have detected gravitational radiation.
There we go, gravitational radiation. So there we go. So there's this, now we have this concept, all right? So before, all the stuff that happened in bent space-time never left bent space-time. It just stays in bent space-time. How what happens in Vegas stays in Vegas, where everything stayed in, all the energy of bent space-time stayed in bent space-time. It didn't go anywhere else, right? Technically. So now they're saying that they've now produced space-time. They've produced a blob of it. And yeah, that's sort of, I don't know if you have. Look, there was one thing when they were talking about the idea of maybe, like I said, the idea of 2 bodies this way, 2 bodies this way, having a different gravitational signature. That's one thing. But the idea of converting their mass into radiation, that's a new concept. So yes, if that's what they're claiming, the conversion of mass to space-time radiation, yeah, okay. Like I said, that's to my advantage, but I'm just saying, what do they really think it's made out of then?
And, this may be a big leap, but, we've just, found the quanta of the 3 other forces of nature, the weak force, the strong force, and the electromagnetic force. These seem like very classical objects, but it's also incredibly extreme conditions. Does LIGO, in this sort of observation, have any purchase on moving towards a quantum theory of gravity?
Quantum gravity, yeah.
I don't know how they could have anything on anything. They have a little squiggly blib. That's what they have, a squiggly blib.
I think the answer is no, but I'm going to, again, yeah, there are theorists on this panel.
There is one crucial thing which is highlighted in the paper that has just been published.
Yes, it matches the simulations. It matches the simulations. So again, it can't be new information because it matches the simulations, and simulations are old information. Can you figure that out on your own? Do I have to explain that to you? This whole thing don't mean nothing. It's like nothing happened because we already had a simulation. We don't even need the realities anymore. I have simulations. Why do I need reality? It matches the simulation.
That is, by very carefully comparing the observed gravitational waveform with the results of solving Einstein's equations numerically on a computer to very high precision, comparing those two waveforms, you can see whether or not the waves got slightly distorted in their shape. As they traveled 1.3 billion light years, they would have been slightly distorted if the graviton, the fundamental particle that carries the gravitational waves.
All right, here we go. We got a graviton now, so I'm in business, right? He said the word graviton. So are we done now? Well, a graviton made by bent space. Bent space now makes energy and it throws it into our dimensions. Okay. Gravitons don't exist, and then you made more of them. No. They never existed before until a couple of black holes swung around each other and made gravitons. Sorry, this is bullshit then.
Had a non-zero rest mass. And through these observations, as is described in this paper, LIGO has placed a stronger limit on the rest mass of a graviton than we've ever had before. That limit, I think, check me, I think it translates in more normal language into 10 to the minus 55 grams. I think that.
10 to the minus 55 grams. So that's what a graviton weighs, apparently, or something. I don't know. Frankly, it weighs as much as a photon, to tell you the truth. Same difference.
It's the number. But
I know it in kilometers also.
Yeah, yes. So
10 to the 16. 10 to the 16.
Can I answer you in a different way? I mean, let's turn your question a little bit. And that is, I think there's a miracle of sorts here already.
A miracle of sorts. A miracle. It matches the simulation. It's a miracle.
For me, there is. I mean, these equations were written in 1915. Okay?
It's gravity, fuckhead. I mean, you know, a lot of these equations were written in, whatever, 16 blah blah Newton time. So, you know, this gravity's not that confusing. Really. You know, it really isn't.
And they've been tested in the weak fields. I mean, you know, many of the tests in general relativity have been done in the field of the Earth, the field of the Sun, solar system. And now also in the binary pulsar, which was the Hulse-Taylor object. And these are all...
Yeah, right. These are all real things. And so this is the first time we've seen the non-real things do something like this. You know, the gravities of the flying pea that weighs as much as 30 suns. Yeah. Mm-hmm.
Well, the strongest fields that we would have are tiny compared to what we're looking at now. The field has a unity strength, if you want to really say what it is, in this black hole system. And nevertheless, the field equations seem to work, which is sort of amazing to me.
I don't know. So it's amazing to him that the field equations work in the field. Okay. On something gravitational.
Tremendous range, a dynamic range of the thing. It's just amazing.
Right, who has a microphone?
I guess you need some special knowledge to be amazed, because that didn't amaze me much.
Let's get a microphone to some of our...
Anyway, I'll be back. Well, that was a little bit annoying. they cut the internet off.
So we took about 4 months of data. Because the signal happened so early, we didn't want to wait until the end of these 4 months before telling the world about it. We needed to be sure, we needed to do our analysis right, so we decided that 1 month of data would give us enough confidence to do that, and those are the results we present. We are analyzing the rest of the data. We haven't seen anything that contradicts anything that what we present for the analysis of 1 month. And we'll tell you more when we finish, hopefully in only a couple of months. It shouldn't take us. We always have coincidences. The question is how significant the coincidences are. We have had coincidences in initial LIGO 2, and they were never significant compared with the expected background in the instrument.
So coincidence is what you said. Coincidences. We have had coincidences. So this is not, that's the whole thing, right? Is you got to figure out what's your probability of coincident, whatever these are. Clearly, they from what they show, they look pretty similar from the two different places. But again, I just don't know how can they know every sound that the Earth makes? Like every burp that the inside of the Earth might make. How can they know all of those sounds? Isn't that what it requires? I mean, they have to know every single possible sound. Every sound it makes every 30 years, every sound it makes every once 100 years, every sound it makes once 1,000 years. They'd have to know every one of those sounds, possible sounds, to know that this is not something the Earth just belched. Or even the sun, the radiation off the sun hits the Earth, causes a blah blah blah. How do they know every one of those? Well, anyway, doesn't really matter. It would be good if they could do the, narrow it down in space a little bit so you could see, because you really will see it. I mean, there's just no way you're not going to miss this one, right? So there's an event that happens that creates as it was called, they did use the word gravitons. 3 solar masses worth of gravitons. And so the local space is going to get really disrupted if it's moving the Earth's surface. Let's see another way to look at this. I mean, clearly gravity is really powerful compared to light, photons. Photons, tiny amount of photons that we're seeing, ton of gravity. But still by scale, I mean, what the energy level is. I mean, are there any X-ray sources or something else you can compare it to? Where there's something that's producing a solar mass of energy in any other electromagnetic spectrum, and then you can make a comparison between the two things and say, is it really possible that if you hit the Earth's surface with that much solar radiation, that it would affect the Earth and warm it a certain number of degrees or do something. But anyway, it doesn't really matter. Yeah, it's all la la la, and they say it does this and does that and blah blah blah. It doesn't have too much to do with anything I'm talking about, much, but just beyond this idea that now they've turned bent space into a concrete thing, in the sense that they're saying they can convert matter into bent space gravitons. I still can't believe he said the word graviton, because I'm still saying, well, what does that have to do with bent space and time? I don't know. Can somebody explain to me the difference between gravitons and bent space? Because I don't know how there can be a difference, realistically. Anyway, until next time and such. That really doesn't make any sense, does it? I mean, you really can't create a separate dimension that creates all the energy to move planets around and then say, and I can convert the matter into the dimension. So you can just squish a planet and make it into space-time gravitons. Is that what he's saying? This makes it sound a little sillier to me, anyway. Why don't you just get rid of the bent space bullshit and stick with the gravitons? Yeah, good idea. Anyway, that's my theory, by the way. So anyway, till next time. Whatever. Scientists are just getting very fluffy. hugs and such.